Good morning, everyone. Yeah.
Cool.
Good. All set now. Perfect.
So good morning, everyone. Those of you here in person, online, I'm pleased to introduce the next speaker, Eneko Aspillaga, who I've actually met for the first time years back in the animals course. So Eneko worked on a range of aspects in terms of telemetry, and I think one of the reasons why he was marked as a very suitable speaker for this training school. So he also works a lot on the ecological aspects, right? In terms of environmental stratification, some dentics like predators on coastal environments, but also has a very good high-level expertise in terms of the technicalities of positioning and telemetry. You know how sometimes people, the more they publish, the more they distance themselves from the practical aspects of the field, right? So usually you remember the name of the tags and which receiver was where, or you do all the high-impact work in publication. So I think Eneko is a good example of someone who's still connected to both sides. And I encourage you all to, beyond just listening, also asking questions. Because again, this is a good example, like some of the previous speakers, who will be able to possibly answer a broad range of questions, from the highly technical positioning aspects to the more down-to-earth practical considerations that you may want to know about. Okay, so I hope you enjoyed the talk, and thank you very much for that.
Thank you very much, Manuel, for the introduction. Super kind introduction. Totally met Manuel, as he said, like in a training course 7 years ago, I think. I was like there, and it's nice that some years later you are like, I have the honor to be a speaker in this training school, so nice how the things change. So first of all, I have, for those that who arrived a bit later, make sure to access the Google Drive folder that Marie sent you, the link, I think, I don't know, a couple of days ago. Or...
Yes. I guess that I wanted to show it. But everybody is aware of the shared folder with training materials?
So good. You have to download the folder that has my name. So make sure that you download it and put it on your desktop or somewhere in your computer. Because this session will be a bit, we will have some theory, but also a lot of coding and R things. So I will be switching from R to the presentation. And it's really nice if you follow this script, also line by line with me. Also, if you find out how skilled you are in R, you see that this script is quite simple for you. You can play with it, you can change parameters, you can see how it behaves. So I think that it can be nice for people that they don't have many skills, but also for the skilled ones, have time to play with it. So that's everybody. Also, for the people in the internet, I put the link in the chat, so you can access it quickly from the chat. And also, if you have any question, any comment, anything, please interrupt me. So it's a bit more dynamic session, okay?
Yeah, and I thought it was a good idea to put the link in the chat. Thanks.
Okay, I
didn't occur to me.
So, does everybody have a folder with my name? And I think that you will have it full of a lot of junk tags that Mac generates for non-Mac users. No, I don't know why, but the important files are the ones that they don't have an underscore here again, okay? Okay, so let's begin. So this session will be on social network analysis. And as we will see, it's a very broad toolbox that allows a lot of analysis, but since this is a positioning, the training school is focused in positioning, we will be based on working on social network analysis from this position data, from trajectories. But you will see that it is super broad, and I hope that the things you learn can be applied if you have some other research questions. And also, I have to admit one thing, that I'm not a super expert in social network analysis. I'm more a user of this toolbox. I think that it's nice because I think that the scripts are a bit nice, user-friendly, but also understand that sometimes maybe you can make some questions that are a bit behind my knowledge. So this is how the session will be structured. We will have like 3 blocks. We'll start with a general introduction to networks, super broadly. And we have one script that we will be running through this block. And then we will enter on how to calculate networks from trajectory data with some example data. This will be the second one. And in the third one, let's see how we are on time. It will be focused on how to do hypothesis testing with this network analysis. We will learn how to do null models that will allow us to test some hypotheses. So we will be using R. Also, if you use R Studio, it's okay. And also, the main package that we will be using is IRAP, which is the main package and done for network analysis. There are many other packages in R, but I think that IRAP really has all the tools and all the functions and the functionalities and metrics that you need to apply it. Okay, and also some if you are really interested on social network analysis, I have those recommendations, those papers. All of them are by Daniel Farin. I don't know if you know him, but he's a super nice researcher and has super nice, those papers are like textbooks on how to apply network analysis. This one is amazing. It's my main guide when I have to apply a network analysis because it explains step by step what to do, all the concepts in a super clear way. And also then it has like more papers that all of them together, I think that they make a wonderful book on social network analysis because there is one focused on how to estimate interactions from trajectories, from proximity, and some others on how to do not null models to do some hypothesis testing. So super highly recommendable references. Okay, so let's start with this broad introduction to networks. Any of you have used network analysis before in your research? Raise your hands, please. Okay, nice. So some few people. So I think that this will be nice for those who didn't use it before. So the network analysis broadly is, as I said, it's a toolbox that allows us to explore the structures that exist in our research system, but based on those interactions between nodes, we'll see. And it's grounded in the graph theory. So it's basically an application of the graph theory. And then we will see what it's a graph and also which advantages it has then to estimate the different metrics. And also it's super broad toolbox that allows us to address a lot of ecological or research questions. For instance, ecologically we can work on how individuals behave among them, like if they like to get together, if they have avoidance behaviors, mating behaviors, connectivity, and also information flows in the populations, or even transmission of diseases. So everything that has to do with some interaction or some relationship between individuals can be addressed with this toolbox. And actually it allows us to calculate a lot of different metrics that then we can relate them with other measures that we can have on the individuals. We can relate the position of an individual inside this population with the fitness, with genetic data, we have genetic data, or any other property that we think might be interesting. So, what is a network? So actually, it's just the observed pattern of interactions or associations. We will see also the difference between both of them because it's quite important. But we have to take into account that also there are some underlying assumptions that we have to consider. And the main one is that actually a network is something that we can observe. And sometimes you have to see if what we observe, to what extent it's a real representation of the reality. So theoretically, we have an observed network, but there is somewhere a real network that may not be. So what is a graph? A graph or a network is represented as a graph. And a graph has two main components: the nodes or vertices, and the links and edges. So what are the nodes? So the nodes are the objects, the individuals, our study focus, and the edges is what define the relation between the different nodes. Okay, so we have those two. We have some nodes. We can see that. Then we will see that these nodes can be almost anything, but it's important that there is something that has to relate these nodes to each other. And also, the nodes, they can have some attributes, so they don't need to be the same. So for instance, here you have different colors, maybe different species. You can see that they have different sizes, they can be different lengths. So there are some properties of these nodes. And also the links, there are different types of links. The most important ones are the binary ones, which only mean that says which nodes are connected between them, just 0 and 1 data. But they can have some weight, or they can have some numeric attribute associated. That can be, for instance, the intensity of the interaction. So these two nodes are interacting in a more with more strength than, for instance, those ones. They have this is just a representation. But and also the links, they can be directed or undirected. So undirected, that means that the directionality of the interaction does not matter. So those individuals are related. It's the same, this one with this one, or this one with this one. But they can be also directed, which means that it's not symmetrical. So maybe this individual can interact very few with this one, but this one with this one can interact more. Anyway, we will focus on just the undirected ones, because those ones, they add more complexity and they are more difficult to handle. And usually the most typical ones used in movement ecology, in social networks, in animals, will be those ones that are just, we have only one value that relates to. Sorry? Also, people in the internet, if you have any comment or anything, you can just speak loud and I will stop.
Hello, good morning.
Hi, good morning.
Myself. Okay. Hi. Everything is clear. I just ask if you could put the microphone just a bit near to you in some way. But everything is clear, both concept and voice. Just
okay, thank you. I will try to speak here close to the.
Thank you to you.
I have the microphone. So
it was just a technical feedback. Thank you.
Good, thank you. So everything clear so far? So actually a network, the basic form of a network, is just an adjacency matrix. This is actually a network. So it's a tabular matrix with n rows and n columns that define the different relationships between them. If it is binary, we only will have ones and zeros, but in this case it's weighted. So we have some numeric values that differ between individuals. And if it is a square matrix always, so we have the same number of nodes here and here. And for instance, if it is an undirected network, as we saw before, what does it mean? That this matrix will be symmetrical. So we will have the same values in the low triangle of the matrix and in the up triangle, because individual 2, for instance, in this case, or node 2, will be interacting with the first individual and will have the same value when we check the first individual with the second one. So it will be symmetric. If it is a directed network, then the numbers will be different. So we will have an asymmetric matrix. And then the thing is that these matrices sometimes are a bit difficult obviously to understand. So networks are usually represented as network diagrams. Those typical diagrams that we have seen like many places, where we have different bubbles, different sizes, and nice links linking each other, and they are much easier to understand and to interpret for a human, from the human point of view. And the nice thing is that in a network diagram, we can play with the attributes and we can put those attributes in the representation. So we can put the size of the individual, as I said before, the strength of the interaction, or also the net metrics that we will extract later from this network. We can use them to represent them. So we will see the individuals that are more important for the network bigger or Okay, so we will start with the first session with a completely an example that is completely unrelated to movement, okay? Which is when it's going to be Game of Thrones. I think that all of you may know. I don't know, have you seen the series?
Yes.
So I think you will see it's also to show that you can do many things with this data, but the basics of the data will be the same, and we will apply the same concepts with animal data later. But I think it's nice also to make clear what the different metrics and everything mean. So go to the folder and open the. Well, if you want to follow it, you can just see what I'm running here. Okay, so it will be this first script that has a 1, it says SNA1, Introduction to Networks. And also, if you haven't done it before, please run this piece of code, because it will install the libraries that we will need. I think most of them, actually, they were already installed those days, data table and some others. So run it, please, so you have all the libraries. If you have any problem, just let me know. I have closed it. So everything, it's okay? Should I move on? Okay. I think I will disappear. It would be nice to have a high table. Okay, so we will load, for this first session, we will load those two libraries, which is iGraph, the one that we will use for network analysis, and also this one data table that actually Henrik highly recommended us to use yesterday. It's an amazing library to load huge data sets. It works super well. So load both libraries. And here you have a function that we will use later. It's just a rescaling function. It will be for plotting reasons, so you don't have to understand it right now. So this dataset that we are going to analyze, it's actually publicly available in this web. Let's go to it. I'm amazed how people has a lot of spare time, I think, and that's those kind of things. So here you have it's network of thrones, and you have social networks of all the seasons and books of Game of Thrones. So the data that we will be using, it's from the first season of the series. This one, we will see what happens with Ned Stark. And the network, here you have, if you want more details on how the interactions between individuals are calculated, you have all the details in this web. But they do it from the scripts. So they took automatically the script for the series, and from the script they are able to know when the individuals are related to each other. People have a lot of time. It's super nice to have those data sets to play with. Okay, so you can load actually the data here from there is also a GitHub account, so you can load the data. But also I put, also run this first. If you are using RStudio, you can run this. It's also something I discovered like some weeks ago, that with this RStudio API library, you can set your working directory to where you have to where this script is stored in your computer. So you don't have to set up your working directory, find where it is. So also make sure that your working directory is in this folder. So you can either download the data running this piece of code, or if not, it is in this in a folder that is in the folder that you have downloaded. So okay, to do a network analysis, we need those two data frames. So we have one data frame, the main one, that is edges, which actually has the interactions between individuals. So here we can open it. So what you have is...
in which package it's content field?
Sorry? Yeah, in data table. Yeah, so you have to load the data table library, this one. So this grid is similar to read CSV or read.table, but it's super fast, creates directly a data table, And actually, if you have some formats in your data, it will automatically understand, for instance, dates or date and time automatically, so then you have to put them manually. So it's also super convenient. So were you able to load this data frame, edges? Yes, no?
Yes.
So what we have here, we have this matrix we saw before. The thing is that it is in a tabular format, so it's a table where we have a source, I mean the two individuals that are interacting, and here we have the number of interactions that are between them. So, okay, here it says Ned and Robert, but they can be fish number 1, fish number 2, for example. And then we have here is the weight of the interaction, and then some other attributes that we can have, and in this case is in which season, to which season corresponds this thing. And it says, if you check the web page, it says that it is an undirected network. So in this case, who is the source or who is the target doesn't matter. I mean, those are changeable. So there is no any directionality on that is interacting with Robert. So it's the same Robert with Ned and Ned with Robert. Okay, and we also have this other table, which is nodes, which it is a separate table where we have the IDs that they are using to define the nodes of the network, and also some labels. In this case, it just uses it to put a nice name for each character. But we would have here the sex of each character, or the age, or whatever other attributes we want to give to each interacting entity. Okay, so let's create our first network with that, okay? So we will use this function that is graph from data frame. You will see that in iGraph you have many functions like this, that it says graph from adjacency matrix, graph from literal interactions. So you have to find the function that matches the data as you have collected it. So in this case it's a data frame, and it will ask this like to just actually it means those two columns are the important ones. So the first two columns will be the nodes that are interacting. And then also iGraph has a lot of functionality, that is, if you have the correct names in the correct places, it will understand things itself. So in this case, we need, if this data frame has a column that is called wave, it will understand that they are the weights of the interactions. The thing is that it has to be lowercase. If it is uppercase, it won't understand automatically as weights. So we have to later tell to the graph like, okay, my weights are here. But if we change the name of the column before, like type here, and now so we have weight with under lowercase, it will understand it at weight. So now we can run this piece of code, and now we have our network set up. And if you can see that now we have an iGraph class of an object of the type of called iGraph. So that was all. This is how a network is done. Good idea. No. Now the nice thing is that with this object, now we can do a lot of things. That's setting it is easy. We will see that actually the problem here, and it's when we enter the second piece of code, is how to calculate those interactions. This is the important thing of network analysis. This is just how to represent, how to manipulate them, so it's quite easy. But then we will see that the important thing is before doing all this. Once we have this, everything goes quite straightforward. So we have then some functions in iGraph that allows us to, for instance, in this case, the nodes are named vertices in the package. So there is this B function that will take all the vertices. So here it says that, okay, we have 126 vertices. This means that we have 226 characters that will be interacting with each other. And we can also check the attributes that we have for the vertex. So we can ask vertex attributes, and we see the ones that actually we have in our nodes data frame. So we have the name, and then this label that was the nicely written name of the character. And we can extract actually those attributes, just asking vertex attributes. And here you can see, so we have first, this is the name, and this is an attribute that always is there because it's the actual ID of each node. And then we have another element that is this other attribute label. We have all the labels here. And if we have more, we will have more objects here. And the same for edges. So we can check, okay, how many edges there are, how many links between characters. So in this case, we have 549 links between characters. And here we have name with Robert, the name is with Jonathan. And same as nodes, we can get the attributes. So we have two attributes, which is weight and season, and we can also extract them with edge attributes. But actually, we can also access all those attributes by using this V function that was extracting as the vertices, and then using it as it was a data frame. So if we put the $sign and then the name, we will get this attribute directly, or label. And actually, we can create new ones if we want. Now, once the network is created, we can now add more attributes, and we can do it by assigning directly it to a new name. So here we have the extra attribute. So now we will have one more attribute, this extra one, which it's just a numeric value from 1 to the number of nodes. There are also some functions that are also specifically to add attributes, but I think that the most straightforward way is this one, just to assign a new attribute. So then from our network, we can recover our data frame. So we can use this getDataFrame function with the network, and we will have back our data frame. So that's also nice if we have an adjacency matrix, but we want our data for any reason that's this way. We can do it like this. We can convert it to a graph and then ask it back a data frame. But also we can create an adjacency matrix actually. So we can run this as adjacency matrix function, and we get, well, we have to convert it as matrix, but here we have this matrix that I showed before in the presentation, which it's a more, this is the real representation of the network. So we have all the individuals here in the columns and rows, and then the number of interactions between each other. And using this function that tells us if a matrix is symmetric, so what should say this? In this case, I saw that it was an undirected one. So yeah, it's symmetric. Yeah, it's a symmetric array. So we have a matrix where the lower triangle and the upper one, they are equal. Also, I didn't say before, but in the diagonal of the matrix, what we have are the self-interactions. So it's some, which is strange in many cases, but in some cases it might be interesting to analyze. But usually in animal ecology, those will be equal to 0. So actually, I think that when we created the network, in this here, no, here actually we just say that it's not directed, so we can specify it here. There is, because I think that there is also another argument that, not here. Okay, I thought that there was also an argument that say, okay, forget about the diagonals, because sometimes we will have computed them and we don't want to take them into account, so we can say forget about the diagonal. It's not important for our network. So no. Okay. Yeah. No, I'm okay with this. Yeah, thank you. So, okay, so the nice thing once we have our network set up is that we can use all this graph theory to extract a lot of parameters in a super easy way and super fast way. So from this network, there are some parameters that they define and that they describe the structure of the network. And we will be super interested in those parameters. Actually, we do all this actually to get those parameters. So some parameters, they are network level, so they explain the general properties of the network. such as just the number of edges, the number of links we have. It's a number, and it says how many links we have in the network. It's a kind of how complex. We can also check the weight distribution. I mean, those weights, which is the distribution of all the weights in the network. Are they super strong? Are they weak? How are they distributed? And also, for instance, another metrics like the edge density, which also represents the complexity of the network, and it's just the ratio between the observed links that we observe between individuals divided by the total number of links that we could have given all the individuals. And then we have some other metrics that they correspond to the nodes, to the vertices. So, for instance, the most simple one is the degree, which says how many links each individual has. So in this case, we will have just one metric for the entire network, and in this case, you have one metric for each node, for each individual in your array. So it's the difference. So the degree, or the binary degree, says just how many interactions you have, how many other nodes are you interacting. And the strength is the weighted version of the degree. So it also takes into account the weight of your interactions, and it sums them up. So you can have a large strength, or by having many little interactions, but a lot, or having some few, but strength. So it just says how strongly are you related to the others. And then also some other centrality measurements that are maybe more interesting also, that says you which is your importance within the network. Those ones already, there are also some centrality measures because they also say how important you are. Usually, the higher the degree is that you have more connections, so you are better connected. Also, the strongest means the same, that you have more connections. Yeah. Okay. Yeah. Sorry?
No, there's a question.
Okay, yeah.
You don't have to stop, just.
There's a question, someone?
Mauricio raised his hand, so if you want to answer it.
Yeah, you don't have to stop. If you want.
I have to do something?
Yeah, we are actually waiting, Mauricio.
Yeah, Mauricio, you have any question?
Question?
Yes, thank you. It was about asking for an example. For example, if I have a relationship between two individuals, mother and son, for example,
Yeah.
should I indicate in some way this in the nodes? Like the weighting the node differently.
I mean, you mean you want to weight the nodes or the edges between nodes? You can then give different attributes to each node. I don't understand what you want to do.
How can I give a weight to this condition? Basically, this is the question. If I have in my network, for example, a mother and a son, and they are often together, how can I stress this in the network?
Yeah, I mean, you can add nodes attributes that somehow represent this. So, for instance, you can create a new attribute for nodes and give them, for instance, a family ID. So if all the individuals from the same family will have the same attribute. The thing is that when you measure the interactions, it should not be, I mean, you should not weight them from some knowledge you have on your nodes. You have to use always the same way to measure the interaction or the association indices. We will see it later. But if you know that they are son and a mother, it is something that you will detect later from your network. And maybe you want to do some hypothesis testing to see if it is stronger or not, but it's not a way that you will give directly. Unless you have, for instance, a network that is a genetic similarity or something like that. You can have, your network can be this, like the genetic difference between individuals. So the individuals that are descendant from the others, they will be super close, and the ones that are not related, you will have higher. But yeah, you can play with the node attributes. I think that's your question, maybe?
Yes.
We will get later into how to estimate. Now here we are just playing with the network. Later we will see how to estimate those parameters and the association indices.
Okay, thank you.
Okay, so we have some other node level metrics, like for instance the betweenness, which actually it says it's a measure on within the network how many shortest path. I mean, shortest path is the shortest path between two individuals. So it calculates all the paths that join every single node, and it counts how many of them go through each node. So this represents how important you are in connecting like this network, like giving like this question to the network. And then you also have this agent vector centrality. There are many other indices, but this one is the sum of the centralities, not yours, but of your neighbors. So the higher the importance of your neighbors, the higher will be your importance too. So it means how well is each individual related to important individuals in the network. But then if you see literature, there are like hundreds of different metrics that can be calculated. But the nice thing is that using graph theory, all those computations are super fast, because using the matrices and matrix operations, it is super fast. So let's see it with the code. It's okay so far? Any question? I know if I'm going too fast, are you following the screen? So, for instance, it's super easy. We have our network. For instance, if we ask the edges and we ask the length of these vectors, we will have the number of edges. This is how many links we have inside our network, and it's 449 and 549. We saw this number before. It also went in the summary of the network. But there is also a specific function for it. That also this count counts you all the edges. We can also check this edge weight distribution. So we can just ask the quantiles, and we have. So we can see which is the distribution of our the weights. Which in this case is the maximum, the individual, which the highest weight is not the individual but the link that has the highest weight is 192, and the minimum is 2. But we can calculate also the median of this, or also check the histogram of this distribution. And also we can calculate the edge density, which is what I said you, that is the ratio between the observed links and the possible links. And usually they are very low values, because of course the most individuals you have in your network, the most possibilities you will have. But it's a nice measure to compare among networks. So all the network level metrics are useful to compare different networks. But then the node level parameters, they are nice to compare those individuals inside the network. So it depends on if you are interested in comparing networks or checking what's happening inside our network. So also there is a function for any metric you want to get. So with the degree function, you will get the degree. So here you have the degree, I mean the number of interactions of each individual for each name. And we can also check this distribution of the degree. So we see that there are a lot of individuals that they have very little interactions, and that there is some few individuals that they have a lot of. I wonder who is, since there is one character here super well connected, we will see who is. Also the strength, the same. So here we have this way version of the degree. So it's the sum of all the interactions that an individual has. In this case, as our network is based on the direct number of interactions. This is the number of interactions that each character has, no matter if they are repeated in the same way. So you understand this difference between the degree and the strength? So if this one has only 2 links with 2 characters, this will be a 2. But if one character interacts 42 times during the session, and with the other one 53, this gives 95. So it's different from the 2 that we can have. So they give a different view of the importance. And also the betweenness. So we ask the betweenness. The event vector centrality, we can also calculate it with this function. And we have those numbers for each individual. And also there are some other, for instance, the page rank algorithm. This is the algorithm that Google uses to rank the pages in the internet. And it's a bit similar to the eigenvector centrality, so your value depends on the importance of your neighbors. It's a bit more complicated to calculate, but just to show that you can calculate a lot of metrics, and you have to find the metric that you think that suits your research question. So now what we are going to do is to take all those metrics, the node metrics that we have calculated, and we will see which characters have the highest values for each metric and see the difference. So we will see better the differences. So here we will do a panel with several plots, just run all those. It's a problem of using RStudio, also Henrik told about this. Okay, so here there is a plot with the characters, I'm showing just the 5 characters with the highest values of each metric. So you can see that in all the cases, the most important one, that is the one below, is net, which makes sense, I think, for the first season, makes sense. That net start is the most important character of the array. But then we can see different differences. So I mean, in this top 5, we usually have like the important characters of the main characters of the series. So we have Tyrion. Actually, I'm very bad with the names, so maybe I don't remember the names of the them. But it's interesting because those two are quite similar. Actually, they are more or less the same. The names has some, even if it has less interactions than, for instance, than Rob, those interactions seem to be more strong. So it's better positioned in with this metric. And if we see the betweenness, remember the betweenness, what it was? It was your importance in connecting the array. Here we have a new character that is in second place, which is Jora. I don't remember who was Jora, but it makes sense that it's important. So it's not an important, doesn't have a lot of interactions. Those interactions, they think that they are not as strong as the others, but somehow it's an important character because a lot of shortest paths are going through him. So that means that it's connecting like separate parts of the network. You remember who's Jora?
It was that last line that somehow protected Daenerys later on.
I think that it's a character that goes from one part to the other, and it's like the link character, maybe it's between plot lines. And then here also we have some other characters coming. So for instance, in the eigenvector centrality, which means how well are you connected? I mean, how influential are your neighbors? You have, for instance, here little finger. I mean, it's not important in any of the others, but here it appears that it's well connected with important characters in the system. So that's I think that's a nice example, because maybe if you have seen the series, you can get what's happening here. But you can see that each metric gives a different value for the importance of the network, of the individual in the network. Everything clear? Any error running the script so far? So now also we will, very quickly, we will see how to plot those graphs, because it's something that is complex, and I think that I would like that this script will help you in the future if you want to plot the graphs. So those are things that I struggle like for several days when I have to do it for the first time. So here you have some tips on how to do it. So if we just plot the network, the first thing we see with iGraph is I see nothing here. So, okay, let's start changing things. So here you have in the script the explanation, like a more wide explanation. But for instance, what we're going to do, in this case, we are going to change the size of the vertex of each node to be linearly with its per scale. It will represent the betweenness of each individual. Okay, so we will use one centrality measurement to scale the size of the bubble. And also,
Sorry for interrupting. Please, can you point with the pointer?
Yeah, sorry.
Yeah.
Okay, so here.
Sorry for interrupting.
No, thank you very much, because
I was losing the point. Thank you.
Yeah, sorry, I'm forgetting people on the internet. Sorry. So here we are just giving the size of the vertex will be scaled according to the betweenness of each individual. And also, for now, we will take those labels because they are messing everything up. So now, okay, so now here we have something that, okay, we see that there are some nodes that are bigger, some of them that are smaller. Usually the main ones are usually placed in the center of the network, and the ones that have less connections, they are outside, but still doesn't look like very nice. So also to change those variables, we can use those with a bit of last, sorry. We can use those arguments in the plot function. In this case, usually it's depending of if we want to affect the vertex, I mean the node or the edge, it will start with vertex or with edge. In this case, it's vertex.size, so it's quite understandable that we are going to modify the size. But actually, if we add to the network itself a new attribute that is called size, this is the same as before. When I plot it, it will automatically understand that I want the node size to be equal to this new argument. So here I have added a new argument to the vertex. So I don't have to write this every time. And the same with labels. Here we are going to change the labels that were appearing before, these huge names, with the label name that we have in our nodes object. So now, okay, it's a bit, the names, at least they are not those uppercase names, they are now the nice names of the individuals, but still we have to modify this to make it a bit more understandable. So we will scale the size of labels. Also, you will use the strength of each size. So the label will be scaled with the importance of each node within the according to the strength that we have calculated before. This here is something we calculated before. So just by adding a new attribute that says label sex, once we plot it, okay, so now we have different sizes of labels. So now we have the node size represents the betweenness, and the label size represents the strength. So we are showing two different metrics for the nodes in the same plot. Still, we don't see anything. Okay, and here we are going also to scale the width of the edges. So we will add a new attribute to the edge, to the link, that will be the width, and it will be scaled according to the weight. So that means that the links that have the higher weight will be thicker than the ones that have a lower weight. So here I also remove the labels to see this. So now you can see that there are some links that are thicker than others. So this represents that here there are two individuals that are very highly connected, and the thicker the line, the less strong the connection. And then also we can change the layout. How iGraph thinks that it's the best way to represent the graph. So here also you have a lot of layout options. You can run this help layout, and here somewhere in the help you will find. So here you have all the different layouts that you can use, and each one will make different decisions to represent all the nodes. So in this case, there is this one nicely that tries to put all the nodes in a nice way. Also, I did some other changes here. You can then change, play with them. But here I also added some curvature to the links to make it more organic. And now it doesn't seem, but it changed the layout compared to before. Okay. Now we will manage to get a nice plot. I promise that. So here you have, going back to the presentation. Okay. So for instance, here you have also a visual representation of the different node level metrics. So here you have the degree that we have calculated, the centrality and the eigenvector centrality, to see that they are not correlated with each other. Depending on the structure of the network, they might give very different view of the importance of each individual. And another nice thing of networks is that sometimes the network has some internal structures. So there are some nodes that are more highly related to each other than other groups of nodes. And also with these techniques, we will be able to cluster our nodes on these communities that are identified by the network. So also you have, if you go to iGraph, there is this function, with this help page, you will have like an explanation of the different algorithms that you can use to make this clustering. There are a lot of algorithms. We are not to see it like in detail. Here I'm going to use just this algorithm, and this one will create a new object that is called communities. So actually what has done is, based on the network metrics, it has grouped the individuals depending on how connected they are to each other. And if we ask this membership to groups, we will have all the individuals classified to which group they belong. And the nice thing is that we can use this to plot. Well, we can here make a table, so we have here some communities. The first one is the bigger one with 44 characters. There is one also with just 2 characters, so depends on the network. We can see how many groups has identified the algorithm. And the nice thing is that we can, when we plot before our network, we can provide this grouping object, and it will show the different communities in our network with different colors. So this is a representation of the individuals that fields that are more connected. But now we can use this to give our own color. So here what I'm taking this group membership and I'm giving a color to each node depending to this group. So I get rid of those polygons. I personally don't like them in this case. So now when we plot it, now we can see the different communities that are within the network with different colors. And now finally we are just going to make a plot and export it, because here the problem is that the size of the plot is too small, so everything gets super stacked. If you run this piece of code, you will export this plot, and it should be now here. Okay, and now in this case, now we can see a bit better the different communities and the characters. So what we see is that there are some characters that they are they have higher, the size represents the betweenness, so the bigger, the most important in the network. And we can see the different communities, and just looking at the names, do they make sense, more or less? So we have here a central one, that has to Ned, Sansa, Joffrey, Robert. So this was the King's Landing, maybe people that was in King's Landing in this season. Here we have the people from the Night Watch, maybe. So they are more related to each other. So it actually is representing the different plot lines. And up here we have people in the Westeros, like really apart from each other. And here the important part of Jorah is that it's connecting this part of the network with this one. And I don't know who is we. We there's another color, whatever. Okay, more or less it's clear so far. I think here you have some tips. If you want to do at some point representations of networks, here you have how to change all the parameters and try to make them. It's true that it's difficult to get really nice networks with R. I mean, it's a bit limited. So if you want to get really beautiful networks, maybe you have to find another software. There are some external free softwares, but well, I think that the nice thing of this is you can repeat it as many times as you want. And also here you have
yes, only one comment, if it's possible.
Yeah, sure.
Okay. As following my first question about the familiar relationship and stuff like that, from your approach, it seems that it's clear that you don't need any a priori assumption, since all the network is made by the observation links observed, but then links observed through observations, right?
Yeah.
Okay. It was just to clarify this and remember it.
Yeah, but in this case, if you want, for instance, you could, if you know that the link between two characters, they are like son and daughter, it's different. You can add a new attribute to this edge and tell, okay, I know that they are a son and a father. So for instance, I want to represent the familiar relationship in another color. So you can do it with the attributes, just for representation.
Yes, it's in the representation, but it's just data representation, not part of the analysis. I mean.
Okay.
Okay, perfect. Thank you.
So here you have a chunk of code that you can run. It uses ggplot and gggraph. So if you are ggplot people, I personally prefer to use the base R, but there's people that they prefer ggplot. So you have also some insights on how to do this with ggplot, which I have to say that at some point makes things also sometimes nicer. So here, for instance, here is a plot where the characters actually are placed in the network depending on the centrality measurement. So actually I use the eigenvector centrality that we calculated at the beginning. So the characters with the highest values are in the middle. And so when we move to the edges of the network, they are the individuals that have less importance in the network. So it's they are like concentric lines. So it's like you can write here some concentric lines. So they are going from the most important ones to the less important ones. It's another representation that also you can explore if you want.
I have another question.
Yeah.
Okay. If you don't kill me,
it's okay.
Is there a possibility to center like a specific node, like a specific name between them? If you go to the previous slide, I can make an example. Like
This?
Yes, can I, in spite of NED, can I center, for example, wheel?
Yeah.
Is there a way to do it?
Yeah, you can play with the layouts. Actually, you can even give the coordinates in which you want to play each, you want to plot each node. So you can you can play with this, but it's a bit you have to play one by one, changing the coordinates. But it's possible to make a table of coordinates, of plotting coordinates of each individual. And maybe there is some layout that does this, that you can say center, but now I'm not sure. But I know that this layout thing is super flexible, so you can do almost whatever you want.
Okay, thank you.
Okay, so this was the first introduction to networks. I hope you enjoyed it a bit and you understood what a network is. But now we are going to get inside the real problems of networks, that is how to calculate the associations between individuals. Let's go back. And specifically, we will talk on telemetry data. So actually, the network analysis is something that has been applied for several years in telemetry data. And actually, we can divide the studies in two kinds of approximations. Because you can use, for instance, the typical thing that has been done in the traditional telemetry data, where you have receivers and you have some detections in one receiver and then in another receiver, is to apply some spatial networks. So in this case, what do we consider a node? In the spatial case, so it's the case you have here. Yeah, so each receiver can be a node. So, and then we will see how the detections move from one receiver to the other. That's one approximation. But also, we will be more centered on the social network analysis, where we will use individuals as nodes and we will calculate their associations. So actually, this has been quite used to measure. Actually, you can get also spatial, as Robert introduced yesterday. You can get spatial. The metrics in a spatial network will be representing the spatial variability of the movement. So you can get here also a lot of metrics that will explain movement behavior of fishes, not the social one. But the problem is that, okay, if we want to do social network analysis with the traditional telemetry data, this is a bit more tricky. Because the nice thing of telemetry, the first thing is it has some advantages, and the first thing is that each individual is super clearly identified. So there is no mismatch of individuals. which it's a problem that maybe people working with mammals, in that they have to go to the mountain and see. Sometimes identifying individuals can be a bit tricky, or birds, if you don't see the ring properly. So we don't have this problem because we know always which individual is each individual. And actually, and also we can track a lot of them together without having to stay there. But here comes the problem, is that we have large detection ranges. So with a large position and the uncertainty, and sometimes if you want to say, okay, to study interactions between individuals based on the co-occurrence of detections in the same receiver, we are making a big assumption, and it's that those individuals are interacting, they are close to each other. But actually we don't know it. We have a large detection uncertainty, and maybe they are detected by the same receiver, but they can be hundreds of meters apart from each other. So that's a problem we have, and actually there is this article by Muriel, and they compare actually how the detection range influences the network that you obtain. How you measure the associations will depend also in your setup. So that's why it's something that has to be taken quite carefully when applying social network analysis with telemetry data. And also we have to always keep in mind that we are not usually tagging all the individuals in a population. So there are some individuals, we are only seeing a part of the network. And there is a large part, usually the largest part of the population we are not measuring. So it's something also that we have to keep in mind. But here, the nice thing on positioning, that's what this training school is on out, is that we really reduce the uncertainty on the position. So we can know if two individuals are really close. If we have a nice resolution tracks, for instance, we can know if two individuals are close. Also, there will be some assumptions here, because also being close, are they interacting or they are just eating from the same, I don't know, algae or whatever, for fish. But at least it's an assumption that maybe it's a bit more, makes more sense, because at least for interacting, usually you need to be close to each other. So if you know that two individuals are quite close, you can make an assumption that they are interacting, but better than interacting, I would recommend to use associated. Instead of talking about interaction, talking about associations, because we are not observing the interaction. And that, I think, it's a problem, because usually social network analysis has been traditionally applied to real interactions that have been directly observed, for instance, with baboons, with birds, that you see that two individuals are interacting. So here you are sure that they are interacting. But when we apply to these non-direct observing systems, we have to maybe be more broad in our assumptions. So I will usually use association. I know that two individuals are associated because they are co-occurring in the same place. So, and actually it's true that also with associations, two individuals are close. Maybe sometimes we are not identifying real interactions, but also maybe we are also, it's a broader view of the interactions. I mean, we are not only keeping in mind that the interaction is one monkey eats the flea from the other one, but here it's like, okay, they are together, so we can get a broader view of those interactions by just using this association. So usually when we have trajectories, the typical way to estimate the associations of individuals, so these links between individuals, will be based on proximity. That's the easiest way. So if two individuals, I can calculate the distance between two individuals and they are close enough, I will consider, okay, they are associated. But also here there is another assumption, that is that which is a threshold to define an association. I mean, should I take it, if they are closer than 10 meters, 5 meters, there is an error also in positioning, so I have to take this into account. So usually we have to avoid using arbitrary thresholds, but somehow finally we have to use some kind of arbitrary, I mean, there is no either, like this is a threshold. We can do some analysis and check different thresholds and see how the network changes to choose it, but usually I would recommend to do something that makes sense with your positioning error, and also maybe the body length of your individuals. So if you have large individuals, you can assume larger thresholds, distance thresholds, but if you have small individuals, you want to make sure that those individuals were really close. And then from those ones, we measure that two individuals being close will be like one association. But then usually we will use some association indices. So we will then somehow, the most typical ones, they indicate the amount of time that two individuals are associated. So the most simple one will be this one, which is when, well, also not this one. So we have the number of moments in which we have observed two individuals associated, divided by the entire tracking period. So it includes the time that we have observed this association, the time in which we have observed both individuals but not associated, but also the time in which we have observed only one individual, and the times that we have observed only other individuals. It's really one ratio. But this is one that, in this case, we're including those terms, and here is that this means that we know that when the individual was not observed, it's because it was not there. So we have the 100% certainty. If some individuals may be missed at some point, so if we only observe one, we don't know if it is because it was there, but I don't know, it was behind a rock or there was a signal collision or whatever. So we can use the halfway index, which actually lowers a bit the importance of this term and makes a bit more balanced estimation, or also just use, okay, I only will include the time periods in which I'm certain that I saw both individuals. So I divide the time in which I saw those individuals interacting or associated, and the time steps when I observe those individuals but not associated. Because sometimes maybe if in telemetry, I think that sometimes you don't know what's happening when you don't detect your individual. Maybe it's in the rain, but it's I don't know where, it's in acoustic shadow, whatever. So any of these, I think that will work in a similar way. So it's clear how we can calculate associations, more or less. Now we are going to do it. So we are going to go to the next script, and here I put for you an example dataset from one experiment we did in Mallorca. So it is a high-resolution telemetry experiment that we did with a super dense receiver array and a lot of hundreds of individuals being tagged there from this species, the pearly razorfish. We have a couple of publications on this study, so if you are curious, we have here the links. We use those microtransmitters from loading. But actually, they were super tiny because it allowed us to also tag like super tiny females. And so we have a large part of the population tagged, from large males to the small females. Okay, so let's open the second script. We can clean the environment. Okay, now we will need some more libraries, so make sure that they load correctly. Also, we need same rescaling function. So first, we will load this table that is fish ref. It's the reference of all the individuals that we have tagged. So this is all the individuals that we are monitoring. We have this data corresponds to a single tracking day, so I just choose one day, and it's the data. We have all the individuals that were tracked in this day, that were 153, with the ID of the tags, the sex, because the nice thing of this species is that you can tell the sex of each individual, and also the length. So this is our node table. So it's the table of the nodes of the network. And then you have the tracks. So tracks is a trajectory data. So you have all the trajectories, you have 100,030 positions just for a single day on those individuals, and actually they are positioned every minute. It's like a simplified data set, not to use because the real one we have a resolution of 2 seconds sometimes, because the tags were emitting in a super high resolution. So here I just put 1 position per minute to make things a bit faster. Let me know if your computers start hitting a lot and burning. But I think it should be okay. And when I tested it, it works. So we have the X and Y positions of individuals every minute. Actually, this data is already post-process it. So I applied this, I don't know if you know the continuous time correlated random walk model, which there's a package called crawl, and it allows to adjust a movement model to your actual track, and then you can interpolate like regular times. So it's super convenient for this kind of analysis. So we have, as I said, 153 individuals. More or less, we have 92 females and 61 males. And so we have for each individual, between 665 data points and almost 900 data points. So here you have, like, let me clean them. Okay. So actually, most of individuals, they have a lot of data points, and there is some individuals that for some reason they have maybe a shorter tracking period, so we have some fewer detections. So here I'm just getting the time interval of the, between detections of the same individuals, just to see that actually most of them they have just 1 minute interval. This is the maximum and the minimum interval between the positions of this individual is 1 and 1. But there's some individual that seems that for 22 minutes disappears. So it's just one individual. It won't give us any problem. And also with this, we are seeing the number of. This is for this day. The number of individuals that are being tracked each minute. So how many positions we have per minute during the day. And as you can see, this fish is super nice because during the night they got in the sun, they burn. So we don't get any position when they are sleeping. So in the morning they start waking up, but they don't wake up at the same time. So here there is one, maybe that the first one that woke up, and then at some point most of them they are awake. And also during the night, and it's super interesting because during the night they go to sleep in an hour where, it doesn't take that long to go to sleep. So all of them just go to sleep when the night arrives. So this is just big to check how many individuals we have each time, because we don't want to do our network in periods when we have few data from individuals. So it won't make maybe sense to include this data in analysis, because here we are just tracking some few individuals. So here I just put a cutoff. I know it was a 90-something% of these values. So we are going only to include in this network analysis the periods in which we are tracking more than 130 or something individuals. In this case, it's not dramatic. It will be more dramatic if we have like ups and downs here, but here it's not going to be a problem. And also here we have the time range of the trajectories. So it's because it's in UTC, so it's from actually the sunrise to the sunset. Okay, so here I'm going to subset this set of data. I'm going to remove this first early morning moments that only some fishes are active, and also the late ones, to make sure that we have a strong data set with most of the individuals already there. Okay, so here I'm using this random color function to just assign different colors to individuals. So you can play with this to see what's happening, but actually I'm just assigning an orange kind of random color to the females and a blue kind of random color to males. So when we represent it, we will see clearly if it is a male or a female. And here with this short code, we are going to plot all of them. Hopefully it will work in your computer. Okay, so here, this is the trajectories we are working with. So each different color is a different individual. In blue, they are the males. In orange, usually are like smaller trajectories, females, and then also we see that something is happening here, something weird. We will see it later.
Quick question, how do you rescale the plot so you can see the excess? Because if you run the
clean your plotting region. So go to the plotting region, and there is a kind of brush because this is because we changed it before with iGraph. If you clean the plotting region, then you will get again. Did it work? You see the brush here, this one.
Yeah, yes, it works. It works.
Click here and then run again.
It works. Thank you.
Okay. And then also we will do some zoom to check it better. Okay, so this is how trajectories look. So usually we have this home range of territorial behavior, it seems, kind of. So we have these males just moving in their patch, with some females also moving, sometimes overlap with males, sometimes with no, and then we have then some crazy females doing crazy things. So this is how our trajectory looks like. Okay, so now let's go into the important part. We have to calculate associations from these trajectories. So what we will do is look minute by minute. We will calculate a distance matrix between all the individuals. So we will know the distances about all individuals, and then we will choose for each minute. We will assign one association to each individual that are, I think that here I will use a threshold of 3 meters, which is more or less the error of the positioning system. Also, it's a small character, a small species, so it's a quite assumable threshold. We can also try to do it with lower one, with higher one, and see how it changes. But for now, we will just stick with this 3 meters. So to calculate these distances between the individuals, we are going to use the SP package, which is a package to work with spatial objects. So what we are doing here is we are going to convert our tracks to a spatial point data frame. It's a special data frame that has some trajectory. It has the coordinates, also the coordinate data. So it's a shapefile now. As for if you use GIS in other things, now we have converted our data frame in a shapefile of points. Okay, why? Because, well, then also we will extract all our single times. So those are all the single 1 minute steps that we have in our data. And what we are going to do is going to do a loop where we are going to run one by one in those times, take the positions of all the individuals, calculate the distances, see which distances are below this threshold, and just return a 0 and 1 matrix for each time step. So here it comes now the hard part. So this, I will run it. It should be quite fast. So here you see it's running. This is a kind of counter, so it says which minute it's processing every time. So mine has already ended. So actually what we have now is a list of matrices. So this is 153. This is the matrix that we are getting. Okay, this is for a single minute. We have one matrix for each minute. Is it working?
Yeah.
So we have for each minute this matrix, which says the distance between the individuals. So for example, let's see an individual that is not still awake. This is the first minute, I think. So there are some individuals missing, but some few of them. But then it says, okay, so this one and this one are in 55 meters from each other. So on, and of course in the diagonal, the distance between themselves is 0. And it's also a symmetric matrix. So the values in the lower triangle of the matrix are the same as the values in the upper one, because the distance doesn't matter which is the reference. So in the loop, if you see the code, I'm using this gdistance function. And that's why I use the SP package, and I converted my data frame into a spatial point data frame because I can use this distance. And actually this distance actually gives me a matrix, an adjacency matrix of all the points that I have with the distances of each one between them, and in a super fast way. More or less clear this loop. What is this loop doing? I'm doing more things inside the loop. You can check them, because also in some points maybe I don't have all the individuals. So also inside the loop, what I'm doing, I'm extending this data frame to include all the individuals and include those NAs where my individuals are missing, because then what I will do is to sum all the matrices among them. So okay, we have this super list with all the distances. And what we are going to do is using this abind function is we are generating a huge matrix. Now we have a three-dimensional matrix. We have the first dimension are individuals, the second one also individuals, but then now we have a third dimension that is the time. So we have now, it's a kind of volume of data. And the next thing is that now we have just one object. This is that we have now 153 by 153 by 824 minutes that I have measured in this. So now with this object, it's super easy because now I will just make a copy of this object just in case I do something wrong. So I define this threshold of 3 meters. So all the values in this matrix that are higher than this threshold will be assigned a 0, and all the values that are below will be assigned 1. And now I will use the apply function that will allow me to take all the third dimension and sum all the values to make a two-dimensional matrix again. So here in associations, see now we have, this will be like the number of associations that we observe for each individual, for each pair of individuals. So of course, one with it's always interacting with itself. It's always close to themselves. And then here we have the number of minutes in which we have seen this individual and this individual together. It's actually 0 times. We have not seen them together. And actually here we have, for instance, one that we have seen them 7 times, one that we have seen them together 1 time, 2 times. And here I also calculate this observations matrix, which actually is a sum of all the values. So it's just to calculate this index that I show in the presentation. We know how many times we see them, but also now we have a value of how many times we have seen them interacting. And actually this observations matrix is the same size, but it says all the values. And in this case, almost all the time that it has 24. It's all the time steps in which have observed both individuals in the array. So by dividing them, I'm using this single ratio. Now I have my association index. So here I have, this is the association index for this day for those individuals. And this is my network. Now I have something that I can use to create a network. And actually I can make an image plot, a heap plot of this, and I can see, well, of course the diagonal is always 1, and then, well, let's see which individuals more or less are interacting. Now we will see it better with them. Okay, so now, from now it's what we did before with the Game of Thrones, now we will do it with this. And from here is everything the same. So we have used, in this case, graph from a data matrix, because now we have the data in a matrix format, not in a data frame format as before. We will say specifically that it is undirected, so it will just take the lower or the upper, but not both of them. We will also say that our diagonal is false. I don't want to take into account the diagonal because it's once and it's not representative of anything. So I'm not interested in self loops of someone interacting with each other. And also I will say that, yeah, these values actually are the weights of the interactions. So I have to say it's weighted. So we do this. We can check the attributes, and in this case, the only attributes are the column names. So we have the only attribute we have for the nodes is the ID. Actually, our IDs correspond to our node table, because I mean the order was actually just 5. We needed to have the same order. So the next thing is that as our nodes correspond to each row in our reference file, we can assign all the attributes in this table directly to the network. So we will add now the sex of each individual. So now we have the sex inside the network and also the length. Actually, here I'm using the two different ways of assigning attributes. It's what I said before. We can use this vertex function with giving a new attribute and assigning it the new value. Or also there is this function vertex attributes that you can say, okay, to this network I want to add a length attribute and the values are this one. They are equal, they are the same. There are two ways of doing this. Okay, and also here now what I'm going to do, and I think it's a bit related to what Mauricio asked before, I'm going to also give an attribute to the links. Because I'm interested in knowing if a link is between individuals of the same sex or not. So I will give, here actually the easiest way I found is to, so I'm extracting the data frame from this, so we have all the edges here, so this individual with individual, this is the way. Here I want to have a new attribute, which will tell me if this is a male-male interaction or a male-female interaction. So this is what this part is doing. So here, now we have a new type attribute. And each edge has this attribute. So now I know if this is a female-female interaction, male-male interaction, and this will allow me also to split my network into the network of males, the network of females, and also the network of males-females. Because in this study, we're interested in knowing which is the social structure of this population. To see if the males tend to stick together, they tend to avoid themselves. Also, males, what happens with males and females. And the nice thing is that we can now split this network and study them separately. Okay, let's take out the females and let's see what happens with the males. So now I can add a new attribute to do this. And we saw this before. Now we can take those two centrality measurements, that is the two simples that we saw before, the degree and the strength. And now I have, and actually I can plot them as a box plot. So now this is, for instance, the degree of all the individuals. So females, this is the values of the female individuals, the degrees, and the males. So we have a measure, it seems like, well, they are quite similar. Maybe males have more interactions than females. Something to be here. I think it's super important. But if you see, we see the strengths. So this is the sum of all the weights. Now here we see some differences. So we see that the males, even if they have the same amount of interactions as females, as we saw in the plot before, they seem to be weaker interactions than the ones that they have females in general with all the individuals. And here, for instance, okay, so this. And here I'm extracting the number of interactions of each type. So I have a lot of female-female interactions, which actually makes sense because we have more females than males. So this also depends on what we are measuring. Then we have a lower number of male-female interactions between different sexes, and then the lowest number of interactions that we have seen are between males. And we can do the same with the weight of those links. So this plot, the plot before was just the number of links, and this is the value of those links. So also we saw this that since that well, here we have those two, the links between males and overall the links that have a male somewhere seem to have lower values than the links between females. So this is already telling us something about the network. And here I'm doing what I said. I'm just removing from the network. I'm creating a new network by removing all the vertices that are females. So I'm removing the females. So now I have just a new network with only the males. And now I will do another one with only the females, and another one with only the males. And now I can calculate in those two networks the same parameters as before, but now for individuals within each type of interaction. So here, this is the degree of males interacting with males only, considering how many male interactions each male has. The same for females, and also this is the interactions of both males and females, but with the other sex. And now I can also plot it. So this is like, those two are different networks, but those are the same network. But well, I can see here the males will interact only with males. They have like between 0 and 3 interactions. Females seem to have like, or very low, but also they can reach a lot of interaction. I mean, they can interact with many females. The males interacting with females, they have this range of degrees, and also the females with the males, they have quite similar, so it's quite reciprocal. And the same, but with the strength. But here also we can see better that, for instance, males with males seem that they are interacting actually. We saw that they have few interactions, but also they seem to be weak. And the highest ones seem to be a bit the ones between females, and between males and females is seem to be quite equal. Okay, and now it comes just a part of plotting the network. It's quite similar to what we did before. Here it's like plotting it looks like something nice, but okay, let's give some colors depending on the sex. So blue ones are males, orange, red ones are females.
Hey, Eneko,
Yeah.
do you mind going back to the previous box plot?
Yeah.
Because why would the number of interaction, the strength of interaction between males and females and males be different?
Yeah, because actually, yeah, no, because this is the strength of males, only males, with females. And this is of females with males. But here I'm only taking the males, and I'm only considering the females.
Okay.
So they don't need to be the same actually.
Okay.
Because I'm only taking a part of the population and another part of the population. Okay, so also I change the plotting symbol also depending on the sex. The size depends on the size of the individual, the size of the plot. I mean, here you can dig into the code and see what's doing it. And okay, here we can see everything very clear, but this kind of super concentrated part of the network that are for females that seems to be doing something together. We can also do this community analysis, but with many individuals and many links and things, it's a bit of kind of mess. So one thing we can do to make a nice representation of the network is to cut this network. So we have to be careful doing this, because I mean you can chop your network, but only for representation. So you can make a clear representation of which are the strongest links that I'm watching. But we should not do this before getting the metrics, because we are getting only a part of the network. But to represent, I'm just going to remove all individuals that they don't have any interaction, for instance. So this simplifies a bit the network. And I'm only taking the edges, the 25% of the strongest edges. So I'm interested in knowing which individuals are really strongly connected. So I'm going to remove all the weak edges, and I'm only going to keep the strong ones, just to make a plot of something that is a bit easier to understand. So here we can see better. We have this female party here, but usually what you see is that each group has one male, which is strongly connected with some females. We almost don't see any strong tie between males, not even between females, and the strongest ties actually are usually between males and females. So here what we are guessing is that they may have some kind of haremic structure. So we have males interacting with some few females only, but males don't interact between them because they are territorial, and females, seems that some of them are doing something here, but in general they are not doing anything. Okay, so this was this part of the script. Here I'm saying all the things that we have done so far, because we will use this script in the next one. But I'm a bit short of time finally. I was expecting it.
Well, I think that we can have another 45 minutes, but it's up to you.
I don't want to.
We have a break.
We have a break
session.
between
If
your
you choose to,
Okay.
we can lock the door and just keep on going.
Okay.
But if you want to take a break, we can take
Okay.
a break now.
So are you okay? Are you following this?
It will be later, probably 11:45.
Okay, I will try to be this part faster. I mean, it's not. I think that the most important things have already appeared. So should I keep going?
So guys, do you want breakfast or keep your?
So, okay, we have seen some patterns here, but now we have a problem that we want to know how representative they are. We want to give, because we have observed something, but then we need some statistical test to know it is representative, it's not. Could it be given by chance, given the size of the movement, the extent of the movements? So there is also this whole part of just how to do hypothesis testing from network analysis. So the problem that we have in network analysis is that they are not independent from each other. So this actually breaks out most of the tests that we can apply to this. They are complicated because actually when we have one interaction between two individuals, we know that the reciprocal interaction will be the same. So values are not independent. So the typical way the most used way to do a hypothesis testing is based in null models. So this is basically creating some new networks where we will break the assumptions that we want to test to say, okay, we will do some random networks that mean nothing, and we will compare these null networks with the actual values that we are obtaining in our network. So, and also there are some approximations that can simulate data. Okay, if my hypothesis is that the movement is this one, I can even create new data sets and then try, okay, where I will break the assumption of males and females being together, being more random, so we can also simulate data, but there are many ways of creating null models. And the nice thing is that we are going to create a large amount of null models. So we can create thousands of them to see which is, okay, if our assumptions are not fit, which are the values that we will expect, and then we will see our value, where does it fall in this distribution. And if it falls outside the distribution, we can assume that, okay, this is not a random interaction. This is something that is not happening by random chance. So the steps are more or less those. We have, first we have our data, we create our network, it's what we did now. We have already made some plots of this network. And we have to choose a test statistic, which is the value that we will use to compare against the random models. So there are different statistics that we can use. If we can use a network level metric, but also to depend on the hypothesis that we want to test. So for instance, it can be if we have some hypothesis on for instance, the importance of the different nodes given an attribute. For instance, we want to know if males are more social than females. What we can do is in our network, we can apply a super simple linear model, for instance, and use the slope of this model as our test statistic. So we know we have this measurement of the influence of sex in, for instance, sociability. And we have this test statistic. Or it can be also the mean, for instance, if we're interested just in knowing if the network is not random, we can use just the average value of one of the parameters. So we can use the mean degree, or also calculate some coefficient of variation, but we need one value that will be our test statistic. Then we will create our null networks many times, and we will start using the same procedure as here, the same test statistic. And then we will just compare the distributions. So here is where also things can be more complicated, because it depends, we can do this data randomization at different steps of the network analysis. So the typical one that has been used in most of cases has been what is called network permutation. So we create our network, and the permutations, we are going to do them inside this network. So for instance, the most typical one is we have some IDs of our individuals. We have some attribute related to each individual. We want to know if, for instance, the individual B, the B1s and the C1s have lower or higher sociability. What we do is to shuffle the labels. So okay, let's see if the males were not in our case will be like shuffling the labels of individuals. So it doesn't matter if they are males or females. They would be like kind of random network. The thing is that then our well, then the values, the association values that we will get will be the same, and we are only going to switch the labels. So finally, the network structure is the same, and this for some hypothesis testing might work, but for some others maybe not, because here the only thing that we are taking about is that we have different levels of each different type. I mean, the amount of individuals in each group is the same. The nice thing that this approach does, but it can produce a lot of false positives and false negatives because it's very restricted to the actual associations that we have seen. So a new approximation that has been proposed lately is to conduct some pre-network randomizations, which is to do this randomization before constructing our network. And this is so with our data, with the data that we are using to calculate the associations, permute this. And this is nicer because also we can control very well which assumptions we want to test. But it's also a bit tricky because depending on the data, it's a bit complicated to have a formulation on how to create a null model. For instance, it's very used when people work with a gambit of the group approach for sociability, that you just are seeing groups of individuals together, and every time you see two individuals in the same group, it's an association. So what they do with a network randomization is to switch individuals from groups randomly, and then create new networks from here. So the new association indices actually will be different too than the ones before. But for trajectories, it might be more complicated. How do you formulate a model that makes sense, that breaks the assumptions that we want to test, and that can be a bit tricky. This is what now I say, that the network permutations, that usually they are norm-based permutations, just changing the labels. And what you do is to redistribute the attributes among the nodes. So, and sometimes it's the easiest way to do this analysis, and it may work in some types of analysis. But they are more interesting in the network permutations, which are made before. So for instance, now I'm going to show which is the approach we used in this study, because we saw in the network that there were some patterns of interactions. It seems that males were less interacting among them than with females, and whatever. And we wanted to see if it was okay. Is this random? Is this chance? They used to have quite a small home range, so is this something that can happen just by chance or not? So what we did actually was we wanted to do some permutations, but also we don't want to break our trajectories, for instance, because in some places they have made changes in the trajectories, for instance, changing the ID of trajectories. But actually this is a post network. I mean, it's the same as changing the labels once a network is done. But for instance, if you have tracks and you want to know if they overlap or no, or whatever, what you can do is to change for instance, if you have several days, you can change the date of the trajectories. So you are breaking the possible correlation that you have between those trajectories in that day, because maybe that day there was some current, there was some weather, something that was doing this to happen. So if you change days, because your hypothesis is that each day they behave differently, so it's a kind of create a random network. But the approximation that we used was looking this several plots ago. We saw the trajectories. Okay, so you see that those trajectories are quite. Okay. Okay, so trajectories actually are quite restricted in the space, and also all the trajectories are quite restricted both trajectories are quite close to each other, so they are quite territorial, but also they are close to a kind of this area. So approximation to see if the patterns that we observed were given by chance was to just, okay, let's redistribute those trajectories to break the possible interaction that is happening between individuals. So we take all the trajectories out, we throw them randomly in the same space, and let's see if we get the same patterns or not. So this is what we are going to do in the next and last script, the script number 3. Actually, just to make sure you can remove everything in your environment, load all the libraries, and here there is already an object that has the objects from the previous script that we are going to use. Just in case you didn't manage to get to the end, here you can just kind of come back to what you should have got from the previous script. So what we did to make this for a network randomization was to calculate the average, the center of each trajectory, of each individual, from the trajectory, from the actual trajectory. So here you have the centers of all the individuals in our data. Then we will define a minimum convex polygon just to restrict. Okay, so this is my span area, there's a bit crop just to. And then what we are going to do, we are going to redistribute all those centers randomly inside this area. So actually there is a function that does this here. It's written here, random tracks. You can just run the function to. And if you run this function, the random tracks function, and running it here, every time you run it, it will create a new data frame with trajectories, but these trajectories will be now displaced from where they were originally. To do the second plot. So it's like playing into the dice, like in a casino. Okay, let's throw the dice and let's see what happens. Here, of course, in this specific case, at this day, we have this kind of collective movements of females. So here, what we say, okay, trajectories are in the same area, but now they are like distributed around. Actually, there are some few females that are covering the range, but actually, what you see is like a similar pattern like this that randomly distributed in our study area. So what we do now, I have encapsulated some of the code from the previous script in some functions to apply them easily. So actually this is a function that will calculate the adjacency matrix. It's exactly the same code as in the previous script, but just inside a function. So now when I run this function on some trajectories, it will calculate automatically our association matrix. So it's the same as before. So now I have a null association matrix, which looks like association matrix that we got from our data, but here the numbers are randomized. And then there's another function that what we'll do is to create a network from this. I mean, it's to do things faster. I don't know what's this. I'm encapsulating chunks of code into functions to make it quickly. So now I can create easily with just one function a new network. You don't see anything. This is a network like the one before, and I can also estimate the parameters for this network. So this is what we are going to do. In this case, we are going to intersect the average, the mean. So we will calculate this average, and this will be our test statistic. So now I'm going to put all those functions that I show you inside in a loop. And it's going to do, every time the loop runs, it's going to create a random trajectory, it's going to calculate the association matrix for this random trajectory, and it's going to create another network, and it's going to return me this new network. So if I run this, here I say 3 times, so from 1 to 3.
Repeat, please, because...
Yeah. Sorry, what do you...
Thank you. And the last sentences, because when you speak with the face on the wall...
Sorry, yeah. I will speak with the... So here I have made some functions that will do this randomization process. So there is a function that creates random trajectories, then another one that will calculate the adjacency matrix from those random trajectories, and then another one that creates a network from this association, and then it will return just one network per iteration.
Okay.
So if I run this, you see now it's running once, it's running twice, and it's running for the third time. So now I have a list of networks. So for instance, now I have 3 networks in this null network list.
Okay.
So, and now I can access each network one by one. So this is the first network, the second null network, or even calculate the parameters for each network. So this is the degree from the first random network. This is for the second one, for the third one. I can actually calculate the degree distribution for the random network. And here what I'm going to do is use another apply loop to calculate the mean degree of each network. So this one actually will give me 3 values, and this is the average degree that I'm obtaining from each network. This is a way also, a kind of trick on how to do iterations in R. I don't know if you have used the apply functions, but they're super powerful to make iterations. So here what we are going to do is to do this, but 500 times. Could be 1,000, will be more correct to 1,000, but it was just a matter of time. Don't run this part, please, because it will take some long. But for this, I have already created this object, which has those 500 iterations. So you can directly load it. So here we have 500 random networks. So later, I also do another function where I'm going to separate the networks by sex, as we did before, and estimate my test parameters. Now I'm not going to get inside this function, but it just separates the function, and it will estimate the number of edges in only male networks, the number of edges in only female networks, number of edges between males and females, their weight, their mean degree between males, the mean degree between females. I mean, all the parameters, I will have them in just one data frame. So I can run this new function to my observer network. So I have here, those are my observer test statistics. Actually, the thing is that here I'm doing a lot of them together, not to do it by one. So here I have those are the observed parameters for my actual network. And here, when I run this, I will get the same parameters, but for each random network. But it's the same data frame with the same number of columns, but this is each one is one iteration of the random network. And here is a function that calculates the p-value of my observed parameters. So it just takes it will look if my value falls outside the 95% confidence interval of the random networks. So if it is further either to one side or the other, this is one is not taking into account if it is directed or not, it's lower than 0. So here it means that my observed parameter, there are no any null values that are larger or lower than this one. So this one is far from this distribution. But for instance, with these parameters, it seems that they are not. No, sorry. Yeah, no, here I calculated the p-values, and those are the p-values that are actually lower than 0.05. So it's telling me which test statistics are actually significantly different from the random networks. And here I'm getting the ones that are not significantly different. This is a bit like that, but let's do some plots and we will see it easier. So now we'll plot some histograms with the, okay. So now I think it's a bit more clear. Here we have network level parameter, yeah. So I'm plotting here, I don't remember which parameters were they. I think they should be, yeah, they are, I think that they are the degree and the, so this is the distribution of the random parameters in the null networks, and this is where our actual parameter is. And actually here, if it is in red, it means that it's significantly different, and if it is in blue, it's that it's not significantly different. Yeah, so this is the number of edges, the number of connections between mails. What we see is that randomly, we would expect to have less interactions between mails. But we are seeing more than what we would expect if the tracks were randomly distributed in the array. The same for females and the same for males and females. So it seems that there are more, well, we are seeing more interactions that we would expect by chance. But interestingly, if we see the strength of those interactions, if we have a random, if tracks were randomly distributed across the study area, the strength of interactions between males, we are seeing lower values than the expected ones. So males are interacting more, with more males, but at the same time with less strength than we would expect. And for instance, for the interactions between the strength of females among females and males with females, we don't see any difference, so they could be driven by chance. But here we're seeing that there is a kind of avoidance between males. And actually, how do we interpret this? Is that they are territorial, so territories are placed in an order manner in the field. So you have one male and you have several territories of males, so you have a lot of possible interactions sometimes with those males, but those interactions are not really strong because they are each one is keeping their own territory, inside their own territory. By chance, we will have like more overlap between males, and more overlap between males will mean that maybe you will have less males overlapping, but they will be overlapping like in a more strong way. So it's why how we interpret this is like males are trying to avoid each other, so each male has some punctual contacts with other males, but they are super punctual because each one is keeping their territory. Is more or less clear? I'm aware that I think that I'm losing some people in this last part, so I'm also doing it quite a bit fast, not to get over time. And this is for the node level parameters. So this is the same as it's the same information, but here we are seeing the mean degree of males. When interacting with males, the mean degree of females interacting with females, and we see the same. That the most interesting thing is that this opposite pattern in male. Actually, this one in this case is not significant, but we are seeing the same. That males are interacting among them like in a less intense way. More or less clear this part. I think you have also the script, so feel free to play with it. I also would like that you can use those scripts sometimes maybe for some guide on how to do iterations in R. So just sit down with time and with everything. I think that there are more comments in the. But this is more or less how we can do some hypothesis testing with acoustic telemetry using this pre-network permutation approach, which actually is not still very extended, because the easiest way, I don't do this in the script because I feel it's quite easy, so you can try to it that is swapping the labels of each node. It's super easy, straightforward. You do this, you mix them, you calculate the node parameters, and you do the same. But this one is more strong because we are testing this hypothesis that, okay, if individuals are just arranged randomly in the area, what will we expect? And I think it was everything from my side. I don't want to burn your brains more today. If you have any question or any... Yeah?
The plots of the networks that you get, are they somehow spatially correlated to where the fish actually are? Or it's just representation?
No, it's completely the same iGraph chooses where to put each individual. You can set up the layout, as I said, but actually it could be done. I can give these centers of home range, for instance, to each node. Mm-hmm. I can force the network to put the nodes where I want to put them. So I can give some geographical coordinates to each node if I know that the fish is somewhere, and make this. The thing is that I have many individuals super close to each other in some places, so they overlap a lot. Some of them not, so it doesn't look really nice. But if you have like a nice distribution of all the individuals, it can be super nice because you will see it. But more or less, what you get is this spatial pattern, because finally it's the individuals that are closer to each other. So maybe it's twisted because it's random how they put but the spatial structure will be more or less what you see in the field. But you can force it to be equal to it. Yeah?
Yeah. Excellent presentation, Nico. Thank you for this introduction to network. You touched very briefly on incomplete sampling, for instance. A problem is not a problem in your system because you have this very stationary place. What if you have a lake with thousands of individuals and you tag in a good study hundreds?
Yeah, no, I think it's a problem too. I mean, we tag a lot of individuals, but most of individuals in the population are not tagged.
Okay.
So this is some, the things that I can make some interpretations. This is just interpretations that are only valid for those individuals that I have observed. So if I say here that the degree of, I have estimated that each male has contact with 4 females, is what I observed, but for sure it has contact with many more. So it's just also all the hypothesis and how to explain everything has to be, you have to acknowledge which are your limitations. So you can say like this RM-like structure, they have, I don't know how many females because you didn't observe all of them. You know that the maximum number of females that you have observed is 6, for instance, with a male. So you can say, okay, I know that at least can have 6 females within an RM, but you can say they are more or less because you should tag every individual, which is actually impossible.
Thanks.
How do you deal with data? For example, if you tag like 20 individuals or 30, and then sometime later you go out to the field again and tag some more.
Yeah.
Do you deal with the data the same way as if you had tagged them all in one day, for example?
Yeah, you should. That's a problem because if you don't see, I mean, if you don't have an interaction, you can't estimate these interactions if you are not observing individuals. So you have to keep. And actually, for this paper, what we did is to choose a sample of data where we have maximum number of individuals for most of the time. So we have to cut some in the beginning, some in the end, just to focus on those days where most of those individuals were being observed. Maybe if you lose one individual, it's not a big deal, but if you have like half of individuals that appear suddenly in the middle of the experiment, I think that it's difficult to handle, at least with this approach. And maybe you have to do 2 different networks for each period.
Thank you.
Any other question in the internet? There is a hand, twice.
Yes, for sure.
You can speak wherever you are.
Hello, good morning. My name is Esmeralda. First of all, congratulations for your work and thank you for the talk. I would like to ask if you consider that social network analysis can be applied to group individuals into groups of different migratory behaviors. Considering that you have a pit tag, daily pit tag detections over several years, for example.
Now I don't have in mind what is your like setup, but I see it like difficult
to apply
to behavior in this case. I mean, as long as this behavior has some kind of social or association component, maybe yeah, if you have, but I don't should be checked like more carefully, but I think that it's a bit strange. I mean, if you calculate, you can know that some individuals are more, for instance, are more associated than others, and then if you know that those are moving more, it's something that you can do a posteriori with the data you get from the network. But I don't see how you can say those migrate more or not. You can only say they are more associated or not, or the network is more complex. I mean, you can only answer questions regarding the network structure.
In this case was more about the presence and absence in a place. So during several years, so the ones that always return, or they do different behaviors like being absent and then present. Was just looking for that.
Yeah, the thing is that as long as you are able to calculate some association matrix, you can apply then the network analysis. The thing is that I don't see how you will calculate these associations in your case. I mean, you need some discrete observation times well defined and see the associations for each of those times, and then, I mean, you can create a network. You can create a network actually from anything you want. We did it with Game of Thrones, you can do it with Twitter data, and all of that. The thing is that you need this data. You need to be able to calculate somehow the association index between each pair of individuals. So as long as you can do this, I mean, you can also, for instance, in the classical telemetry studies, it's true that you can get some spatial metrics from the network, because actually the network is a representation of some spatial feature. So you can calculate distances, for instance, within the network in that case. But it's a specific case and it's not a social network analysis. So I'm not sure, maybe something can be done, but now, like with this information, I see it difficult to apply.
Yeah, thank you. Thank you very much. I agree.
Maybe anyone in the audience has something or knows something about it. Okay, thank you, Esmeralda.
Thank you. There are some questions in the chat.
Yeah, the chat.
No, they just said great talk. Great.
Okay. Well, it's also
Right. We can read them aloud.
yeah.
Thank you. Okay.
So if we don't have any more questions,
Okay.
What you presented here represents 1 day of data.
Yeah.
Right? How would you go about testing the temporal stability of your network?
Yeah, actually, we did it in our research.
Okay.
What we did this separately for each day, for instance, and then we checked. I can show it to you maybe. So this is the same network, but with the entire data set. So this is for all the, not only considering 1 day, but all the days together. And then what we did also to check to the temporal variability was this, to do it day by day, separately. And then check our daily networks, how they change every day. So here we see that, for example, this is the female networks. For most of the year, they are not very different from what random expectations, but then there are some specific days where our values they are higher, much higher than what we were expecting, and that was because of some very punctual aggregations that they do, but like the one we see in the tracks that I showed you. But it happens only, so you can detect, okay, there is something happening on those days. And this was our approach, to do it separately for each day and see the temporal variability of all those values. But this was our approach, and I guess that there might be many other approaches.
Thank you.
Yeah.
I was wondering that for testing, if we're testing an hypothesis, you could also, instead of generating random tracks within the whole polygon, you could generate random tracks within each species of the single individuals.
Yeah. And the thing is that our tracks are not random. They are randomized,
Yeah.
but the track structure is exactly the same because we only have displaced the tracks.
You only display.
Yeah, so the structure of the inner structure of we wanted to keep this structure to make sure that, okay, given the same structure of the track, let's see what happens. So they are not completely, we just randomized where tracks were especially, but not the track. But also you can do some, if you have some good modeling and you are able to get a model that creates plausible trajectories, you can also randomize it that way. But you mean to do it inside the
the whole range of the individuals, because then you would it would randomize kind of they would still be there because that's where they are,
Yeah.
and then you choose their social interactions and associations. Like that. And then you
Yeah.
see this is
Yeah, it depends on the hypothesis and also what, which is your theory about how it's working it, because in our case, I think that those, the contacts between males from different, that have non-overlapping territories, they might be by chance actually. So the fish is inside, but at some point, one fish is close to this corner of the, because they are actually super small home ranges actually. They are like just 10 to 20 meters. So it's not super large. So the fish actually can move quite often. Actually, it's moving all the time around the entire network. So I think that is just when they are getting close to the neighbors, just might be by chance. But also it can be nice to test, to see if really there is. This one will test a more precise hypothesis to see if real individuals, when they are inside, they look to each other like in a very precise way. So it could be also nice to test.
because I was thinking of this because you actually, but the home ranges are so small, you have the whole home range.
Yeah.
Whereas for other species, actually, not the whole home range.
Yeah, it's another hypothesis. It will be another hypothesis, a more detailed hypothesis, but it can be also that. It's okay? So thank you very much for
Gary, thank you.
listening. Sorry if in the last part I was like too in a rush. It was like I thought that I would have more time.
Well, there will be recording, so everybody can.
Oh, maybe that's because we skip this part.
Yeah. Thank you very much.
Thank you very much.
It was really nice. Yeah. We've got a couple of homeworks now. Read or watch the Game of Thrones. And a build a Haven. Okay. Okay, guys. So see you in 25 minutes, and we will have a virtual talk this time from Eneko.
I don't know.